Good morning, students. Today we are going to start the second lecture on the theory of elastic failure. We have discussed the other theories uh, like principal maximum shear stress theory and maximum distortion strain theory in our previous lecture. In this lecture, we will be discussing the other theories which are used for the elastic failure of the material. The first one is the maximum principal stress theory. This is also known as the Rankine theory. It is used for brittle material. Used for brittle material. Uh, this theory says the failure occurs. This theory says the failure occurs. The failure occurs when maximum principal stress, maximum principal stress uh, developed due to external applied load, external applied load uh, exceeds the stress at the elastic limit. Uh, so this is a statement of the theory that the failure occurs when the maximum principal stress developed due to the external applied load exceeds the stress at the elastic limit. So for this, let us consider a stress element. Consider a stress element. So it is having a stress sigma x in the x direction, sigma y in the y direction, and sigma z in the z direction. So these are the normal stresses in x, y, and z direction respectively. So this is z direction, this is x, and this is y. So the principal stresses can be given. Principal stresses. So it is noted by sigma 1, 2. This is equal to sigma x plus sigma y by 2 plus minus under the root you can put the half here, sigma x minus sigma y whole square plus 4 times 6. So maximum principal stress is maximum principal stress, that is sigma 1 sigma 1 is equal to sigma x plus sigma y by 2 plus half under the root sigma x minus sigma y whole square plus 4 times tau. So this is the maximum principal stress, and the minimum principal stress will be equal to sigma 2, and this is equal to sigma x minus sigma y divided by 2 minus half sigma x minus sigma y whole square plus pi square. Okay. So according to this theory, the maximum principal stress is sigma 1. Okay. This should be less equal to the sigma, where sigma is the stress at elastic limit. Stress at elastic limit. Stress at elastic limit. So if you plot this graphically, then at x is equal to 1 and x is equal to minus 1. X is equal to 1 and here x is equal to minus 1. So here y is equal to 1 and here say y is equal to minus 1. So if you draw this, this will give us the region where the material is going to be shaped. So this all region is going to be the shape region. If we design a component and the stress fall within this region, so this is you can say sigma 1 upon sigma from the upper relation is equal to 1 is equal to x is equal to 1, and similarly sigma 2 upon sigma is equal to y. So this is also known as the Rankine theory, as I told. It is mainly used for the brittle material. Now the next is maximum principal strain theory. It is also known as the Saint Venant's theory. So it is good for brittle material. Good for brittle material. So this theory says that the failure occurs when maximum principal strain exceeds the strain at the elastic limit. So that means the failure occurs when maximum principal strain principal strain exceeds strain at elasticity. Strain at elastic limit. So again, if we draw a stress element and this is y, and this is the sigma x, sigma y, and sigma z. So the principal strain epsilon x will be equal to sigma x divided by E minus mu times sigma y divided by E minus mu times sigma z divided by. So this formula you know. Similarly, this will be E1, that is the or epsilon 1 maximum principal strain. Similarly, epsilon 2 will be equal to so corresponding to x, y, z, you can write here. Here you can write. Let me first. So therefore, epsilon 1 will be equal to sigma 1 upon E minus mu times sigma 2 upon E minus mu times sigma 3. So according to this theory, the maximum principal strain, so that means 1 upon E should be equal to 1 upon E minus x mu times sigma y plus sigma z. This should be equal to sigma upon where sigma is the elastic limit of the stress. Elastic limit of the stress. So this theory, as I told, it is for the brittle material. So it overestimates the results for the ductile material. So maximum principal strain theory. So graphically, if we want to represent this, so say for the two-dimensional case or 2D, so you can write here. So it will be like this. So it is a rhomboid. So it will pass through the diagonals, pass through the center. This is rhomboid. This is a rhomboid. So in this case, this will be the sigma, and this side sigma 2, sigma 1, right? So this is a rhomboid which is obtained, and this is known as a shear diagonal. Shear diagonal. So you can write this sigma 1 minus mu times sigma 2. This should be, if it is in tension, then it should be sigma, and similarly sigma 2 minus mu times sigma 1. It should be in sigma elastic limit, where this is a. So this is a second theory which is known as the principal strain theory. Now next is the maximum strain energy theory. It is also known as the Hague theory. It is also known as the Hague theory. So this theory says that for a for a body subjected to complex stress system, failure occurs when total strain per unit volume exceeds total strain energy at the elastic limit. So let us check what is written. For a body to subjected to complex stress system, failure occurs when the total strain per unit volume exceeds the total strain energy at the elastic limit. So if we say here that sigma x, sigma y, and sigma z, they are the principal stress, are principal stress. Okay. Then the strain energy per unit volume, strain energy per unit volume. So strain energy is U and the volume is V. So strain energy per unit volume, this can be given by the relation 1 upon 2E sigma x square plus sigma y square plus sigma z square minus 2 mu sigma x sigma y plus sigma y sigma z plus sigma z sigma x. So this is the strain energy per unit volume. So this is equal to sigma square, where sigma is the sigma square, where sigma square upon 2e is the strain energy at elastic limit. Strain energy, or we can write here strain energy per unit volume at elastic limit. So this is uh, this is a maximum strain energy theory. So this gives very good results for the ductile material. It gives very good results for the ductile material. Just a minute. Let me see if I can do some numerical for you. So, so we let us try to do some numericals so that you can write here. It is good results for ductile material. So let us start some numerical. So first numerical is you can say a cylindrical shell is made up of a mild steel plate. Cylindrical shell. Cylindrical shell is given. So what is cylindrical shell? The thickness of the shell plate is given as 1.2 millimeter, and dia is 1.2. Sorry, this is the diameter which is given. This is a dia is given 1.2 meter. Dia is given, and it is subjected to the internal pressure. It is subjected to the internal pressure P. So let me draw this more clearly. Dia is given, and it is subjected to the internal pressure P. Okay, so P is given 1.5 meganewton per meter square Pascal. Material yields. So sigma at yield point. Material of the shell is given. It is yielding at 200 meganewton per meter square. So calculate the thickness of plate. So we have to calculate the thickness on the basis of the three theories. So number one is according to the maximum principal stress theory, maximum principal stress theory. So the factor of safety is also given. The factor of safety is given as 3. Okay. So we have to find the thickness. So the hoop stress, we'll calculate first the hoop stress, that is sigma c or sigma theta is equal to PD upon 2T. Okay. So this is given as 1.5 multiplied by T is given as 1.5 divided by 2 into T. So this is given as yield stress is given as 200 and the 200. So this divided by the factor of safety, that is okay. So this gives us the from here we can find out the value of T. Okay. So and from longitudinal stress we can find out the longitudinal stress is ED upon 4T. Okay. ED upon 4T. And here P is given, D is given. So it is equal to this is how much I think 180 180 so 0.90 आ जाएगा. So this will give 0.9 upon T. Okay, 0.9 upon T. So we can find out 0.9 upon T is equal to 200 by T. So T is equal to, we can calculate the value of T according to the maximum principal stress theory. So T is equal to, because this will be maximum, that's why we are taking this. So T will be equal to 13.5 if we solve this millimeter. Okay. Now, according to maximum shear stress theory, according to maximum shear stress theory, so it will be sigma C minus sigma L divided by 2 is equal to sigma Y, that is the working stress, sigma Y. Okay, so it is 0.9 upon t we have calculated, and this is 0.45 t. So 0.45 t divided by 2 times t. This should be equal to 200 divided by 6, because 3 was the factor of safety. So according to this, if we calculate t, so t will be equal to 6.75. So this is according to the maximum shear stress theory. So if we calculate according to the shear strain theory, maximum shear strain theory, if we calculate according to the maximum shear strain theory, then it will be sigma 1 square plus sigma 2 square, because a two-dimensional case, plus sigma 1 sigma 2, and this is equal to sigma square or the working stress. So this will be 1 upon t square and 0.9 whole square, first one, plus 0.45 whole square multiplied by, sorry, this will be minus here. This time is minus here. So you can multiply this 0.9 multiplied by 0.45 is equal to 200 divided by 4, right? So if we calculate t from here, so t is coming 11.7. 11 point. So you see, the T is coming maximum according to the shear strain theory, and it is no, it is maximum principal stress theory. So we will take the in order to design the safe pressure vessel, we will take the thickness as the maximum. So this way we can decide which theory will apply. Example 2, one more problem we will do. It says at a point on the machine member, it was found that sigma xx is given. It is given as 150 megapascal. And sigma y is given as minus 100 megapascal. So the yield strength ys is given. Ys is given 300 megapascal. Okay. Calculate the maximum safe value of Txx. So we have to calculate the Txy maximum safe value. according to the Rankine theory and Gusset theory. So Rankine theory is the maximum principal stress theory. Rankine theory. So Rankine theory says that sigma 1 2 is equal to sigma x plus sigma y, sigma x plus sigma y divided by 2 plus minus or under the root sigma x minus sigma y divided by 2 whole square plus tau square. Right? You see, if I have, so this will not be there because I am using the formula half inside. This. So if you put the value here, so you will get 150 minus 100, and that is 50. 50 upon 2 will be 25 here, plus minus 25 whole square. Sorry, this will be 150 and minus minus will plus. So it will be 250. 250 by 2 is 125, and that will give you 15,625 plus tau square. Okay. So this will be the relation. So Rankine theory says this should be equal to 300. Okay. So when you solve it, so you will get tau xy or tau y, tau xy will be equal to 245. How much megapascal? Okay. Now, according to the Gusset theory, so this says sigma 1 minus sigma 2 should be equal to sigma for 2 decays. So it will be sigma 1 and sigma 2. So it will be 2 times under the root of 156 plus tau square. 186 is equal to 300. If you solve from here, the tau is equal to tau xy is equal to 85 or it from 84.7. It is 85. Okay. So you see, according to the Rankine theory, it gives the bigger results which are on the higher side, and according to the Gusset theory, it gives 85. So this way, it is applicable in the different applications. So I think I have tried to cover the extent possible which was required to be covered in your course. So thanks very much. for a patient's listening. Give a